this one? I think Jyoti wants to put it on. That's all. Thank you. Okay, so let's continue. So where were we last class? So at the end of the last class, we were discussing the following. We were discussing how to use, we gave a Hilbert space interpretation to the path integral that defines gravity, that defines the conformal field theory on the two plane. Okay, and at the end of the last class, we were discussing how you can compute the commutation relations between the generators of the Bayes strategy. So let's remind you of the definitions. We have T of Z was equal to sum over n, Ln over Z to the power n plus 2. Okay, this defines Ln, and we make this expansion in the Z plane. Okay, if you want to know what T of Z is in terms of these Ln's in the W plane, well, we'll just apply the usual conformal transformation to tell that. In particular, you pick up a minus sign, apart from the usual shift of anything. You pick up a minus sign because you remember that you picked up a factor of, it would have an expansion up to a shift. It would have an expansion like T of W equal to minus sum over n Ln into the power I n something. I think I've got this plus minus wrong. Okay, the additional factor of minus z squared came from the conformal transformation that worked even for primary field. And then there's also the fact that here in L0 we would add a delta function, delta X0 C by 24 plus sign, as we discussed last class. Okay, but this is our definition. So these LNs, in everything we're doing, are being defined by their Laurent expansion coefficients in the Z plane, and they turn out to be whatever they turn out to be in time. Okay, this is always a convenient way to work, because now once you've got this definition, you don't need to worry about what they were in the W plane. You can just work with this definition, never refer to the W plane, except for conceptual questions. Because for the answer, when we eventually use this, we may want insertions in the W plane, in which case then we'd have to work out what the insertions we're interested in there are in terms of these things. But at least for all intermediate results, we can forget it. Okay? Then we set up the calculation for Lm commutative. Okay? And we said that this thing was equal to integral dz dw z to the power n plus 1 w to the power n plus 1 2 pi I okay T of z T of w where the first term had n acting before and therefore at earlier times than n. So n was associated with w. So in the first term we had this being the w contour and this being the z contour minus the w contour, let's say, is unchanged, and it's the z contour. Okay, and just one more. I mean, before we continue the calculation, just one more conceptual remark. Remember what this expansion meant. As we discussed last class, and this expansion as an operator expression in the Heisenberg picture is just not always correct. However, this expansion is not always correct for correlation functions of t. If you have correlation functions of t, this expansion asserts that t is an analytic function whose only singularities are 0 and infinity. Okay? But correlation functions of t are not analytic functions whose only singularities are at 0 and infinity. In fact, they're analytic functions whose singularities are at points of insertions of other operators. Okay? So, such an expansion is correct where you're not crossing other other operators. Okay, so in computing lm, that's why we have something non-trivial in this calculation. In computing this first guy, ln, we have this, where this is an accurate representation of this quantity in that order. Similarly, this is an accurate representation of this quantity in this order. Had it been that T of Z was everywhere completely analytic, regardless of W, then these two contours could have been happily deformed to each other and cancelled. Okay? So, this is something that's of course very important to keep in mind. That correlation functions of T will not have this form. Are not always analytic functions. They have singularities at points of insertion of other operators. Okay, fine. So let's go on. So what we wanted to do was to do this computation. Fine. Then we talked about our strategy of doing this calculation. Our strategy of doing this calculation was to fix a particular point in W, let's say this point, and then deform the Z contours. Sorry, W. Deform the Z contours so that this one goes to surrounding here and then lying with the W contour, and this one goes to surrounding here and lying with the W contour, so that this calculation was the same thing as the calculation of the Z contour going like that. That contour integral picks up the residue, cancelling one of the factors of 2 pi I, and so we have finally that ln is equal to the integral dw over 2 pi I of something. What's the something? The something is the residue as z goes to w, the residue in z, in the variable z, as z goes to w, of z to the power n plus 1, w to the power n plus 1, t of z dw. Okay, so this quantity is a residue in z, so it's a function of w, and that function of w has to be integrated. Is this clear? Okay, so now let's carry this through. Let's compute this residue. So in order to compute the residue, we know that z to the power n plus 1 is a completely analytic function of z at w, and so the only possible places of non-analyticity, the only possible sources of non-analyticity are non-analyticities in this in the 2-point function between t of z and t of w. Any contribution to this 2-point function that is analytic in z minus w will not give us a pole here, so we can ignore those. So it's only the non-analytic pieces that are of interest to us. What were the non-analytic pieces? The non-analytic pieces were t of z, t of w is equal to c by 12, sorry, c by 2 z minus w from the cube plus 2t of w z minus w from the squared plus del t w.
That's 4.
C by 2. Thank you. Okay, so let's substitute this in. Once we substitute this in, you might think, the only pole is this piece. But that could not be accurate because we've got a double pole here which will give us a pole when we take terms in the Taylor expansion of z to the power n plus 1 about z equals w. So let's write that Taylor expansion now. So z to the power n plus 1 is equal to w to the power n plus 1 plus m plus 1 into w to the power m plus there's a term times z minus w plus m plus 1 into m by 2 into w to the power minus 1 z minus w the whole thing squared plus m squared minus 1 to m by 6 to w to the power minus 2 into z minus w the whole thing cubed. We don't need to go further than this order of the Taylor expansion because the maximum singularity was z to the 4. So this is the largest term that can give us a pole. Okay. So now let's multiply this with this and isolate the coefficient of 1 over z minus w. So we get 3 terms. We get this multiplying this multiplying this multiplying this, and this multiplying that. Okay? So the three terms are c by 12 times m squared minus 1 into m. Okay? Plus this times that side. So 2m plus 1 into t of w plus and we should get our powers of w, right? So this was w to the power minus 2. This was w to the power m, w to the power m, and we also had overall. Right, we have w to the power n plus 1 everywhere. So multiply everything by w to the power n. Because this was going along with that. Okay? Plus w to the power m, and then plus del t of w into w to the power n. So that is this recipe. This is the quantity that we have to multiply by dw by 2 pi I and integrate over the quantity. Okay? Now the question is, well, what is this stuff? Of course, what we're doing is a contour integral of either constant or t. So this can be written once again in terms of L's. Okay? So let's see how we do that. So let's first take to the constant. So the constant term is w to the power n plus m minus 1 into c by 12 integral dw by 2 pi. Okay? Now, all of these are 0 unless n plus n is equal to 0, in which case we pick up the contribution of the pole, namely 1. Okay? So this is equal to delta of n m. Yeah, n is equal to m times c by 2. N minus m. Thank you. Let's call it n plus m 0. Okay, great. Now let's examine the objects. Okay, so the other two terms are actually both very similar and can be converted to each other. Well, let's first write them down. This is w to the power n plus m plus 1 into 2t of w plus w to the power and this is into 2 into n plus 1, I'm sorry. 2n plus 1 plus w to the power n plus n plus power, yeah, n plus n plus 2. Yeah. This thing integrated dw by 2 pi. Okay, now we should really substitute each of these expansions in terms of the power series and L's. There's a little trick that helps. That little trick is an integration by parts. Okay, we've got a derivative of t. We could substitute in the derivative of t in the expansion, but it's even simpler just to integrate this by parts. Okay, so if we integrate by parts, what we get is a minus sign here and the derivative of this. Okay? Now, this minus sign in the derivative makes this power the same as that, but makes the constant, which was here 2 into n plus 1, minus m plus n plus 2, and then the whole thing is w to the power n plus n plus 1 into dw by dt. Is this clear? Okay, so what do we have? This is 2, no, so the 2 is cancelled. So first is 2 and 2 cancel. So we get m minus n into w to the power n plus 1 d of w dw by 2 pi I. And now this is simply m minus n times L of n plus n. Right, because this is the thing you multiply by to isolate out the coefficient there. Remember that t was like 1 was equal to L of m divided by z to the power n plus 2. So if you wanted the coefficient of z ln, you multiply by z to the power n plus 1. Okay? So this is z to the power n plus 1. Therefore, it's in. So we've got both pieces in this expansion. So let's sum up. What have we concluded? We've concluded that Lm, nominated Ln, is equal to m minus n Lm plus n. Okay? Plus delta of m plus n from 0. So these commutation relations are sort of well known. They define what is called the Beer symmetry. Okay, it's a very important. These commutation relations are very important because, as you know, the ln's and ln's are conserved charges. Ln's and ln's are conserved charges in our theory. The commutation relations between the conserved charges defines the symmetry algebra of the theory, just like the commutation relations of the SU2 generators defines the symmetry algebra of any theory with rotation. Okay, so this is telling us what the this is telling us a lot about what we can say about the theory from symmetry. This is a very important relationship. Okay, now there's a physical point that I'll bring up now. And I'll also bring up here at the end of the lecture. I'm a little clear on that. But anyway, let's talk about it. And that's this. Some of you might be worried about the following. I know when I was a student, this kind of thing about Minwalla. Look, a conformal transformation is just a coordinate change. Okay? You might have thought, well, it's just one of these analytic coordinate changes. And so if you want to know what the algebra of these coordinate changes is, should be very easy to determine. You write down a vector field that generates a coordinate change. We know how to do that. We've done it before. It's like z to some power times delta z is the power z to the power n plus 1 or something. Then z is the generator. Let's I won't get all factors, right? So it's something like z to the power n plus 1 times delta z is the generator for ln. So if you wanted to sit and compute the commutation relations of these symmetric things, it should just be computing the commutation relations between these two vector fields, and then you get whatever you get. Okay. So why don't, instead of doing this fancy calculation, why don't I do that simpler calculation? Okay. And when you do that simple calculation, you get an answer, and the answer turns out to be exactly the same as this, but without this factor. Okay. Now this might seem like something worrying. What's going on? If the symmetry in question was that of these coordinate changes, how can the final symmetry algebra not have the attribute of these coordinate changes. Certainly this thing didn't happen in rotations. The generators of rotations will be the same symmetry algebras, infinitesimal spatial rotations. So we demand that they do. It's no surprise. So what's going on? How can it be? How can it, you know, all this sounds very like a lot of fancy mathematics, but how can it make any sense? Okay? And the important point here that is missed by this loose argument is that a conformal transformation is not just a coordinate change. It's a coordinate change plus a wild transformation. Okay? If you make a coordinate change, you also change the metric. Right? So you make one of these conformal coordinate changes. You also change the metric in the theory. And then you have to rescale your metric by a wild transformation in order to put the theory back into a theory with flat space. A conformal transformation, when we're dealing with conformal field theories, you know, when we're making these transformations, we are also changing the metric on which the theory is. So it's a conformal transformation is the product of these two things, these two operations. Okay? Now, in the loose argument, we were assuming that the wild transformation did nothing. Okay?
Is it just product or is it something of the product?
What's it?
I mean, is it just a product or?
It's by product I mean you have to do two operations. One of which is a coordinate change, the second of which is a wild transformation. I don't want to say something about the global structure of the group or anything like that. Okay? So, this part of, you see, the stress tensor, you see, this part of the commutation relation that came from the most singular piece, of the stress tensor, the TTOPE, okay, is actually telling you how T transforms under wild transformations. See, this part is just the transformation of the stress tensor under a coordinate change. Okay? This part does not happen under a coordinate change. If you just make a coordinate change, that's not how T transforms. So it must be, since this is related to how T transforms under a conformal transformation, it must be this part is telling you how T transforms under a wild transformation. So what's happening here is that the wild transformation that is needed to put the theory back into flat space metric is not acting trivially enough. Okay? And it's this additional bit, okay, that is giving us this additional term. Okay? So this thing is completely physical. This part, this transformation is not just a coordinate change. It's coordinate change plus something else. The combination of the coordinate changes is giving us this. The combination of the wild transformations is giving us this. Okay? That's what's going on. We will see this in more detail, probably by the end of this class, where we will use this point of view to calculate. Okay? Well, there's no contradiction. It's all perfectly sensible. It makes sense just if you think about it correctly and cleanly, not loosely. That. Okay. Fine. So this is the Shiraz sort of algebra. Any questions or comments about it? Okay. Now, let us use this Shiraz sort of algebra to understand first what was special about primary states. Or what was special about primary states. Okay, now, whenever I define a term for an operator, I will often, without telling you about it, use the same terms for states. And the understanding is always, this is the inheritance under the state operator. So we define the primary operator as an operator that has, whose only singularity in the TTOPE is that of square term and the linear term, with particular forms of the T operator, with particular forms of the residence, the coefficients. Okay. Now where any state state that is dual to an operator that obeys such OPs between stretched and certain state, and the operator is going to be called the primary state. Okay, I want to understand what I can say about the action of these L operators on primary states. Okay, how do I understand that? Well, remember what a primary state is. A primary state, by definition, is obtained is the wave function that is obtained by inserting a primary operator O at the origin. And we do the path integral up to some point, let's say z equals 1, and we get some state. Fine. Okay, how do I now understand what I get when I act Lm on the state? Well, if I want to act Lm on the state, I should act with the operator. I should act with the operator T of z, z to the pi n plus 1 by 2 pi I, 1 over 0, where this integral is taken over this contour C. What is C? I don't care what it is, it's just some contour that's around 0. We know the answer doesn't depend on what contour because everything's analytic except it's 0. I've got no insertions apart from insertions. Is this clear? Okay? Very good. So, the question is, what is Lm on 0? Lm on O. Okay, let me invent some notation. Suppose I've got an operator O, the state corresponding to that O. Yeah. Put that operator in. Yes. So I'm trying to compute Lm on O. So Lm on O is the state corresponding to this operator. Okay? So all I have to do is to compute what this operator is. Well, how do I do it? In order to do that, I use the OP. Let's see, I assumed here that O was a primary. Soon see what we get if it was not, but okay. Let's assume for a moment that O is a primary operator. Okay, so we get T of Z times O is H O of 0 divided by Z squared plus del O divided by Z times Z to the pi n plus 1 dz by 2 pi I. Because I'm doing this contour integral, I should be picking out the pole. Okay, I should be picking out the pole. That's why I kept only the provided that I've made an assumption. I've made an assumption, this calculation is correct. This calculation is correct provided that m is greater than or equal to minus 1. Because if m was less than that, then I get contributions to this operator product. I will get contributions that involve analytic terms of the operator product. Cancelling the non-analyticity of the implicit insertion technique. Okay? But I'm going to do my calculation only for n greater than or equal to minus 1. Okay? This calculation will only receive contributions from the non-analyticities of the operator product expansion. These non-analyticities are under complete control because this is by function of primary operator. Okay, so that's what we get. Well, we get this term clicks if m is equal to 0. So we get delta m0 times h times O0. This term clicks if m is equal to 1. So we get plus del O if n is equal to minus 1, MO times delta M minus 1, and that's it.
Shiraz, can we just using primary operators span the whole Hilbert space?
Yes, we'll see that in just a moment. In what sense that's true. The statement is that as base is not true, but a related statement is true. Okay. So this calculation was true for all m greater than minus 1. So we get something non-zero only for n equals minus 1 and n equals 0. Okay, so let's describe it. We found that L minus 1 on O is equal to del. Actually, this statement is not true just for primary operators. Completely, it's true in complete generality. So as we said, any local operator, the pole part of the T operator expansion is derivative of operator by Z. So this part just will always be true. We've also found that L0 on O is equal to H times R. Again, this statement is true in greater generality than for primary operator. It will be true for any quasi-primary because it depends just on the 1 over z squared part of the operator. But, so this is rather generally true. These two statements are quite generally true. Okay? But, this statement, Lm of O, this is O not 0, sorry. I'm sorry I used bad relation. This is the state O is not 0. Lm of O is equal to 0 for all m greater than 0. That crucially uses the fact that there were no singularities in the OP beyond inverse quadratic. And it's true only of primary operators. Okay. Now this is a very interesting statement in order to understand what its physical implications are. In order to understand what its physical implications are, I'm going to ask you to remember what these LMs were on the cylinder. Okay. Remember that we had T of Z was equal to Lm over Z to pi plus 2 sum over M. This plus 2 was taken away by the conformal, by the conformal transformation business, and we got a T of W which up to some shift, okay, was e to the power I mw Lm. The important point is the following. L0 is the zero mode of T of W, and when integrated over the cylinder, and when added to L0 power actually, it gives you the energy of the theory on the cylinder. This we've seen before many times, right? Okay? Now let's look at what we got for the So remember the physical interpretation of L0 was the energy of states, or the left moving part of the energy of states. It's really energy plus momentum of states. Okay? Now let's remember what we got from a Shiraz equation. We got the computation relations Ln is equal to m minus n Lm plus n plus m squared minus 1 into m by 12, is it? C? By 12c delta m plus n 0. Let's now set L0 n equals 0. What do we get? Suppose we set m equals 0, we get L0 Ln is equal to minus n Ln plus 0, because the only time the delta function clicks is 0. Okay? That tells us that modes Ln have energy minus n. Okay? So if you act on a state of energy E with Ln, the resultant state has energy E minus n. Therefore, Ln's with all n's positive are operators that lower the energies of states. Whereas Ln's with all n's negative are operators that raise the energies of states. Is this clear? Right? Because this is the minus side.
So this is just telling us that these operators, these states which correspond to the primary operators are the lowest.
Good. So what does it mean that Ln on O is equal to 0 for all positive n? Now let's think a little group theoretically. You see, suppose whenever you have any group implemented in quantum field theory, okay, any algebra implemented in quantum field theory, you can take the Hilbert space of the quantum field theory and decompose it into irreducible representations. Of that algebra. Now, the algebra in question does not commute with energy, but has the operators in the algebra in question, as we just seen, don't commute with the energy operator of our theory. They're non-trivial computational relations, the energy operator. Can both raise as well as lower energies. In the quantum field theory, in a sensible quantum field theory, I mean, we often demand, certainly in every real world, initially we will demand, that the quantum field theory have a lowest energy state. Okay? So, it cannot be in such a system that it can act indefinitely with the energy lowering operators on any state of the theory. Okay? So there must be a class of distinguished states in the theory, such that these states have energies that cannot be lowered further by the operation of the symmetry algebra. Okay? We've seen that these states, such states are exactly primary states.
We have not seen that all the lower states are primary.
Well, we've not seen it in the words we've done, but you can easily run it through the algebra. You see, suppose we had any OP coefficient, let's say it's 1 over z to the k, that will give us a non-zero action of some L with something positive. I've not said it in these words, but it's too an extension of what we've done to see that. Okay?
But okay, so that just says that if it is a quasi-primary, then it should be a primary.
Correct. But we've already argued that it's always possible to use a base. So okay, you're right. You're right. We could, take two primary states with different weights and take linear combinations of them. That would technically not be a primary state. Okay? And would still obey the condition that it is annihilated by ordinary operators. Okay? But what we have argued effectively is that it's always possible to choose, if you take the space of states that is annihilated by all positive L's, then it's always possible, that's a linear space. It's always possible to find a basis in that linear space, such that the basis elements are primary operators. You see, because it's always possible to find a basis which is quasi-primary, and then that finishes it.
Okay, so but that is just stated with the proof that you can always choose a quasi-primary.
In this space, but we've already seen that it's always possible to find a quasi-primary basis in the whole space. Okay, so you now want to know whether it is whether okay, let's see. Well, okay, good point. Though I'm sure it's easy to make the proof. Let's see. Can we do it on the spot? Okay, so you're asking, well, suppose I've got a set of states that is annihilated by all lowering operators. Yeah. I mean, the question essentially is, can you diagonalize the energy operator in that set of states? Is it quasi-primarity? Okay. Yeah, but I think it's more or less clear. You see,
O acting on 0 would mean that the OP between T and O would not have the higher term than 1 by Z square.
That is correct. So that Loeb diagram agrees with. So what he's asking is, could it be? Let me clear this. What he's asking is that, well, suppose we put that condition, then all that we know is that the maximum singularity in the OPE is 1 over Z squared. Okay, so any such operator has the property that T of Z on O is equal to Let's actually make the argument. It's some other operator, right? So some other operator of O tilde by Z squared, okay, plus del O by Z. Okay, and but in our definition of an operator to be primary, okay, we require this O tilde to be the same as O. So you say, how do you know you can all? Okay, I'm telling you always find a basis in such states that where this is satisfied. But how do you know it can? Well, you see, firstly, notice that for this to be true, it must be that O tilde has the same weight as same dimensions. Because T is dimension 2. O has some dimension. So these two sides have the same dimension. O tilde has to have the same dimension as T. As O. And because this is the dimension of this side of the OPE is dimension of O plus 2. We've got the 2 from 1 over Z squared. So this has to have the same dimension as O. Okay? So O tilde is some other, so the state corresponding to O tilde is some other state in the Hilbert space of the theory. Okay? Is some other space in the Hilbert space of the theory with the same energy as O. So what you have here now is now let's try to make a basis change in the space of
so L0, the state O will be the state O. Right?
what?
L0 to the state O will be the state O data.
L0 of the state, exactly. And
so you're just saying that you want diagonal.
then we're just diagonalizing the Hamiltonian in that. Right. Okay. So let me say again what we've concluded. We've concluded that there must exist a distinguished set of states that are annihilated by all energy lowering operators of the theories, LMs with m greater than 0. Okay? And it's possible to find a basis of these states such that in this basis the states are dual to primary operators. Okay. Now given any state in the Hilbert space of the theory, okay, given any state in the Hilbert space of the theory, let's act on it with lowering operators, energy lowering operators. Either you will run up to energy minus infinity, or you will hit one of these states. Okay? So what we concluded is that every state in the Hilbert space of the theory can be reached, that it is possible to take any state of the Hilbert space in the Hilbert space theory and act with a sufficient number of generators of the symmetry algebra and reach one of these distinguished states. we've concluded pictorially. Suppose we take, we draw primary states of these special states which are annihilated by all the lowering operators by these horizontal lines, and try to write down the set of all states that you can reach from these primary states by the action of the symmetric states in the symmetry. What do you do? Okay, you can't act by energy lowering operators in these states, but you can act by energy raising operators. Now, after you've acted by some energy raising operator, you can then act by a lowering operator. But that is redundant. It's redundant because you can then take the lowering operator through the raising operators until you annihilate the primary state and be left with only terms in terms of raising operators by using the commutation relation of the theory. Sort of like we do it with J minus and J plus when we're computing commutators. Okay? So, you can generate a whole set of states by taking this primary state, this low state state, and acting by all energy raising operators in all possible ways. This may not by itself be an unconstrained thing to do. There may be some relations in this, as we will discuss in a bit. Okay? But certainly you can do this. All these states will give you some towers. Okay. Now, you take any of these states here, and by acting with lowering operators, you can go back to the primary. Unless the state is null. Unless something very funny happens, which again we discussed in some way. You know, it's reasonable generically, that you can take any of these states here, act with lowering states, and get to the primary. So this is the structure. Also, it's clear that there's no limit to how high this tau goes. Because you can act with L1 as many times as you want, L minus 1 as many times as you want, or L minus million, L1, L minus million, and so on. You just keep going. Okay?
You are assuming here that the theory is founded from
Yes, that's an assumption. Okay? So the structure of the Hilbert space of the theory, it has this structure. There are these distinguished lowest weight states, primary states, and then you build up modules of the conformal group. Module just means an irreducible representation. Okay? An irreducible representation that you get by acting on this lowest weight state by all the raising operators in any way you want. Okay? All of these objects are related by action of the symmetry. These states are to be obtained from one another by action of elements of the symmetry algebra, so it's the same representation of the algebra. Okay? Things that you get from different primaries are not related to each other by action of elements of the symmetry algebra and form different representations. Okay? So, the structure of the Hilbert space of the theory goes as follows. The Hilbert space is divided into a bunch of modules or representations, each of which is labeled by its primary state. Okay? So the question you would ask in part 4 is that it's not true that you can find a basis in the Hilbert space which is spanned by primary operators, but it is true that you can find a basis in the Hilbert space that is spanned by primary operators and LMs for all positive n acting on primary operators. Since we know everything about LMs just from symmetry, that's good enough for many purposes. Okay? Any state that is not primary is called a descendant. It's a descendant of a particular primary. If you know everything about that primary, you know everything about that descendant. For instance, if you know the energy of this primary state, and you want to know what the energy of the descendant is, well, suppose this descendant was L minus 20 acting on the primary. We know it's an exact statement that L minus 20 has energy of primary plus 20. The energy of L minus 20 of the primary is 20 plus the energy of the primary. So we know the energy of the primary, we know the energy of the state. So if we were interested, for instance, in finding the full spectrum of the theory, if we knew the spectrum of the primary states, that would be enough. Everything else is done by symmetry. Okay? It's also true, some statement like this is also true for correlation functions. If you know these correlation functions of these guys, you can determine the correlation functions of descendants by acting with differential operators some part of which we discussed.
How do we know that we can never have a state which is actually there in two modules? I mean, in both the modules.
Okay, good question. How do we know that this thing? You see, but the basic point is that okay.
I mean, we can go up but come down.
Come down.
But maybe you can come down to some other primary operator.
No. You see, the coming down is the reverse of going up. Okay. There is actually one subtlety associated with null states, which we've not yet gone to, and which is related to your question. Okay? But ignoring that, let's give a naive answer first. Okay, so see, suppose this state was related to our primary by the action of some elements. Okay, so let's say it was L minus M1, L minus M2, up to L minus Mk, acting on some primary. Okay, now I want to check what I get. Okay, I want to check what I get. Okay, firstly, I'm going to ask, is there a way of getting by acting on this state, okay, with lowering operators so that the resultant state is primary? Okay? So now this question is completely algebraically answerable. Because what does it mean for the resultant state to be primary? It means that all raising L's annihilate the state. So I'm going to ask the following question: can I act with some L's, whatever they are, so that the net result is that Lk for all positive k is primary? ABC. That k, there's no, okay, this, that, yes, Lq. Okay, now there is one way of doing it. Okay, and that one way of doing it is as follows. Suppose we choose, lowering operators to kill all these raising operators. Okay, so that we just get rid of all of these. That will do it. But in that case, we just reach the primary P. Now I want to argue that there is no other way to do it. Okay, and the argument goes basically as follows. Suppose you've acted with some raising operators, lowering operators, to kill some of these L's but not all. You can always, suppose you've acted with lowering operators, we'll always take the lowering operators through. When they reach the primary, they kill it. So whatever we have in the end can be written as some number of raising operators on the primary. Either some of the raising operators are left or they're not. If there are none left, then we reach the primary in question and we're happy. But if there is something left, let's suppose there's an L minus 2 left. Okay? Then I'll act with an L plus 2 on this state. Now according to the Shiraz algebra, L plus 2 times L minus 2. Okay, now then I'll take the commutator. This thing annihilates the primary. Okay, so L plus 2 times L minus 2 is something very concrete. What is it? It's 4L0 exactly, plus some C into M into some number. Well, some number. Yeah, okay, 3 by 2. Acting on this state. Okay? Now, unless there is conspiracy, okay, that allows this number to be the same as this number. Okay? Then, unless that is true, okay, then what we get is that it's impossible, right? That this is not true. Now, these conspiracies can sometimes happen. They related to the existence of null states, and what the structure of the Hilbert space becomes then is more complicated. Okay, what happens is that there are some states here, Then what actually, okay, let me just tell you the answer of what happens then, and we come back to studying it in a little more detail. You see, what can happen exactly for this reason that we discussed is that there is a state that is both a descendant of a primary as well as a primary itself. For this reason, that although you can reach it by acting with raising operators on some primary, you cannot reverse that ascent, because the state that would have reversed it actually gives you 0. Okay? But it turns out that whenever this happens, actually we can probably see that quite easily, but I won't try to do that now. So whenever this happens, this state has 0 norm. This state and all its descendants have 0 norm. Okay? So if you're really interested in a unitary quantum field theory, where no physical states are allowed to have 0 norm, you should delete these states from the spectrum. Those states aren't really there. Okay? But either you can take 2 points of view, either it's an unacceptable spectrum, or that it's a mnemonic for a spectrum which does not include the 0 norm states. Okay? Basically in that situation what happens is that the structure of the irreducible representations of the Vega Sourov algebra and special values, see there's a special values of L0 and C. You get representations that are different from the generic ones. These a generic representation you'll be able to act with all the LNs which are raising in an unconstrained fashion. For these representations you act with particular set of elements, you get null states which are just supposed to be 0. And these states are deleted. Okay? So the net conclusion is the same. That even when this happens, there is a single primary for every real state in the theory. Because these guys which could have ended here don't exist. Okay, so this may not have been terribly clear, but we will get back to this at some point. But any questions at the moment? Just to clarify this.
For the Vega Sourov algebra,
yes.
Is it true that for a generic representation without this null states?
Yes.
Is it true that the primary is unique for the Vega Sourov algebra? Or there's only one state for one irreducible representation.
Yeah.
That defines it.
That's yes.
But for higher dimensions,
you're worrying about representations of the. You see the equivalent of the spin. See what happens is that you have a representation of SO D.
right.
Now in this case D is 2. You have a representation of SO2. Yeah. So which is one dimension. Good. Good. Other questions about this? Path, are you at least?
I'm not okay. I noted what the conclusion would be. Now I have to clarify how this comes about.
Fine. Okay. Sounds good. Other questions or comments? Before we go back. Okay. So. Actually, the existence of these null states and these truncated representations is very important because it often allows you to solve these theories. You see, the way you do it is that, generically you get some state by acting on a primary state with enough number of elements. Okay? However, for these special representations, if it's in a unitary theory, so these states are deleted, by acting with these elements of that state, you just get 0. Now we can make the same statement about correlation functions of operators. How LMs act on operators just by some differential operators. Okay? So some combination of differential operators and any correlation functions of these special operators must be 0. So that gives you differential equations for correlation functions of these short operators, which then gives you great control over the solutions of the correlation functions. Okay, but that's a throwaway remark for now, which we may or may not come back to actually. Anyway, okay. Sounds good. Okay, So, any other questions or comments before we proceed? Very good. So that's why primary operators were special. Okay? They were special in the sense of representation. Okay. So now let's move on. Let me now demonstrate something we use in the derivation of the stress tensor OPE. And the something was the claim that in any unitary theory, the scaling dimension of every local operator is strictly greater than 0. And, greater than or equal to 0. And there's a unique operator with dimension 0, namely the identity operator. Okay. That demonstration is terribly simple. Okay. Suppose I have an operator of a given scaling dimension. Don't care what it is. It's always possible to choose a basis of operators that have given scaling, particular scaling dimension. Okay. Let me call that operator O, and let me act with L1, L minus 1, and let's say that O is a primary operator. Let me first study primary operators. So we have L1, L minus 1 acting on O. Okay? By the Virasoro algebra, this is equal to 2L0. There's no central charge term here because remember there was an m at n squared minus 1. N squared minus 1 is 0. Okay? So now let me sandwich this with an O on both sides. Okay? Now this commutator term
just reduce to 1.
It's just exactly. It's just O, L1, L minus 1. Obviously, the other way, L1 annihilates the primary state. And now we reach something important that, let me first make the statement and then we'll have a discussion. L1 is the Hermitian conjugate of L minus 1. Okay, let me go ahead with this statement and then we'll come back for a discussion. Okay, because of this is positive definite. And therefore, with this 2h times O4, this is positive definite. In a unitary quantity. Getting? Therefore, h must be a positive number. Okay? So any local operator in the unitary quantum field theory must have positive scaling dimension. Because our proof of the statement assumed that
O is a primary operator.
that O is a primary operator, and B, that L1 and L minus 1 are Hermitian conjugates. Let's address the first thing. Since we proved that every primary operator has dimension greater than 0, it immediately follows that every operator has dimension greater than 0. Because if there is an operator with negative dimension, and it's not primary, then there must exist a primary with negative dimension. Because you can keep lowering the energy of that operator until you get to primary. Okay? So the first assumption was not restrictive. What about this L1 being the Hermitian conjugate of L minus 1? This, of course, manifestly true. Okay? This is manifestly true because of the way we are doing our quantization. Remember that in the expansion of the stress tensor in terms of W. Okay? What was that? Let's go back to Minkowski space. What did we have? We had T of sigma and tau. The stress energy operator, or even classically, the stress energy function as a function of sigma and tau, was taken as just Fourier expanded. Okay, was taken as just Fourier expanded in the following fashion. So, e to the power I m tau. Well, let's say we had it as e to the power I m sigma plus L m plus e to the power minus I m sigma minus e to the power minus I m sigma minus m L tilde of M. This is summed over M, and let's call this A of the sum over M. Okay, now let us first think of this classical expansion. In this classical expansion, we demand that that T is a real function. Okay? That demand of reality tells us that the complex conjugate of T is itself. But in complex conjugating this function, we get minus Im sigma plus. Right? Because sigma plus is just tau plus sigma. Okay? Similarly here, complex conjugating this function, we get minus Ik Lk. So how do we ensure that the stress energy tensor as a function is real? It's real provided Lm is equal to Lm star. Sorry, L minus M is equal to Lm star.
No, but sigma plus does not become sigma minus.
No, of course not. So there's no connection between the L tildes.
Oh, sorry, sorry.
Yes. And similarly, L minus K is equal to Lk star. Okay? Now, this statement was about classical functions, but of course becomes promoted to a statement about quantum operators. The condition once again is we demand that T be a Hermitian operator. Okay? The same conclusion remains when we replace star by die. Okay? So, in the quantization of the theory on the cylinder, this condition was manifest. And what we're doing on the plane, as we've seen repeatedly, is implementing this quantization in a more convenient path integral. So we're not changing any of the conjugation relations. We're defining a Hilbert space on the cylinder always. Okay? Defining norms and Hermitian conjugates on the cylinder. So none of this changes. Okay? So this is why it's true. Okay. That's why, by the way, we were very careful to define T as equal to Lm over Z pi plus 2. If we didn't have this plus 2, you see, this plus 2 is what relates this expansion to this expansion. Because of the transformation, even the primary part of the transformation between the W and the Z plane. Okay, so you might have thought, why not take T and expand this Lm over Z to the power M? You could do that, but then Lm and L minus M would be Hermitian conjugates of each other. It would be Lm and L minus M plus something else, and it will be a pain in the neck. Okay? So, working with the conventions that we have been working with, when we're doing things carefully, these things are all Hermitian conjugates of each other. And in particular, L1 and L minus 1 are Hermitian conjugates of each other. Is that clear? Okay? So, using this Hilbert space interpretation, we have justified one of the statements we used before, namely that in the unitary quantum field theory, every local operator has positive norm. By the way, let's understand something a little more clearly. Suppose H is 0. Well, that implies that L minus 1 on O is 0. Okay? What does the L minus 1 on O mean? You remember we saw at the beginning of this lecture, that L minus 1 on O is equal to del O. So we come to an interesting conclusion. An operator has 0 holomorphic weight if and only if that operator is anti-holomorphic. Del O, holomorphic derivative of that operator is 0. And an operator has both 0 holomorphic as well as 0 anti-holomorphic weight if and only if that operator is a constant. There's only one constant operator, it's number. Okay, it's the identity operator. Okay, so, but because we've got this holomorphic factorization in our theory, we reach a more sophisticated conclusion. There are interesting local operators in the theory, T is one of them, which are holomorphic. such operators will always have anti-holomorphic weight 0. Moreover, the only operators that have anti-holomorphic weight 0 are operators that are holomorphic. Okay? Any operator that has a weight of the form h comma 0 must obey the equation del bar of that operator. Okay, it's a very important conclusion, so it's worth saying many times. And of course, a cruder version of the statement is that an operator with both weights 0 is necessarily constant. There's only one such operator there. Okay, is this clear? Now, there is. Okay. I had hoped to start on a discussion of. So the plan from now on is, in today's lecture, I'm going to complete every general bit of discussion about conformal field theory. From next lecture on, we'll start discussing specific. So this Friday on, we'll start discussing specific conformal field theories. We'll start with just free scalar theory in detail in this language, and we'll try to see some of these abstract arguments work out in, more concretely. But today we must really complete our general discussion. So there are two things that I wanted to say about conformal field theories in generality, both of which have to do with the importance and First, I'm running out of time, so I'm going to have to do some of this through exercises. Okay, I'm going to suggest exercises for you as outline for logic. Suggest exercises for you to do them, and request you really to do these exercises. Okay, it's the only way we get to anywhere. Really, we're going a little too slow in this course. But okay, fine. Firstly, there's another. I want to suggest the following. You see, effectively, what we did here was to take. Remember, we said that we have primary state at weight h. There's the primary state, and then there are states obtained by acting on that state with L minus 1s. There are also states that you can get. This has energy 1 above that, right? What about states with energy 2 above that, right? Okay. Well, there are two substates. There are two kinds of states that you can get, which have energy 2 above that. These are L minus 1 squared on primary and the L minus 2 on primary. Okay? Now, so suppose we take an arbitrary level 2 state. Okay, so firstly it's clear. What I want to do is try a little bit to understand the structure of inner products between states that are descendants of the same primary. Okay? We've already understood the structure of inner products at level 1. We found that, there's only one state, so there's but firstly, there are no non-trivial inner products between the inner products between states at different levels vanishes. Why? Somebody tell me.
It will become L positive.
Okay, because
F plus N will be positive.
Say again.
So that will give rise to a commutation relation with L positive,
right?
Acting on primary operator.
Okay, that's one way of saying it's an operation. But of course, it's a very general statement that follows from general rules of quantum mechanics. Okay, now which you can prove as follows. Suppose you've got something at level k, so its energy is h plus k, and we're looking at something whose energy is h plus k prime. K prime is not equal to k. Then insert L0. L0 is a emission operator. So acting this way, it produces h plus k prime. Acting this way, it produces h plus k. Unless h plus k prime is equal to h plus k, this inner product is zero. I think that is standard application of quantum. Usual tricks we play with quantum. So the structure of these inner products is only non-trivial between states at the same time. So we've completely understood let's say that we work with a normalization such that the inner product of primary with itself is 1. Okay? We've determined what the inner product of L minus 1 on the primary with itself is. It's 2h. Okay, and we've got a constraint on h from the requirement that this be positive. Now, let's say we go to level 2. Okay? Suppose we go to level 2, we have two states. We'll have L minus 1 squared on O, and we'll have L minus 2. Okay? Now, you can form a matrix, a 2 cross 2 matrix of inner products from these two states. Okay? You form a 2 cross 2 matrix of inner products from these two states. This 2 cross 2 matrix of inner products can be computed by using the commutativity relations of the L's and the Vivassoro algebra. Okay? I want you guys to do this calculation. It's a little calculation. Compute this 2 cross 2 matrix of inner products of states. Now, suppose you have this computation in your hand. Okay? Suppose you have this computation in your hand. What requirement does unitarity impose on this matrix? But unitarity requires that any linear combination, any particular state you take, has positive value. But any state that you take is some linear at level 2, is some linear combination of these two vectors. The fact that every such linear combination has positive norm is a statement about what this matrix is. Matrix of inner products. Technically, it's a statement that the matrix of inner products is what's called positive, which means that it's all positive eigenvalues.
If it is an uncertain coefficient.
Sorry? It's semi-definite states, exactly. Right. Okay, so positive and some perhaps zero eigenvalues. Okay? So, what I want you to do is to take this thing, compute the eigenvalues of this matrix, and demonstrate that positivity requires that the central charge of the theory is strictly greater than 0. That is impossible for both eigenvalues to be positive unless the central charge of the theory is greater than 0. Sorry? No. Well, it could be equal to 0. Perhaps then one of the eigenvalues will be around 0. Let's take that possibility out. Okay? But once you've done this calculation, we'll discuss it a little bit in class next time. What this calculation shows you is that this business of having, you see, we had this, where did we get the C from in the TTOP? We just said, what is the most general possible TTOP? We put that C, but C could have been 0. What this calculation shows you is that C equals 0 is essentially a very trivial theory. Actually, I think we can show that if C is 0, then this theory can have only one state or something like that. When you do the calculation, we'll examine the answer. Okay? So, this possibility that we talked about, by adding this extra term to the TTOP, wasn't just some mathematical nonsense. In order to get something physically sensible, we must have a non-zero and actually positive central charge. Okay? So that's the first thing first exercise I wanted to suggest to you, which I strongly suggest to you. Now there's a second exercise I want to suggest to you, which I also strongly suggest to you. I'll outline the exercise in ideas, and I want you to fill in the numbers. Okay? And that's it. The exercise is, let us try to see if we can understand, well, the end result of this exercise is a very deep result. It is the fact that the dependence of the partition function of a conformal field theory, path integral of the conformal field theory. So far, we've been studying the conformal field theory in flat space, but we can study it on any metric. Okay, the dependence of the partition function of this conformal field theory on the metric of the theory is completely fixed merely by the central charge. I'm going to write, by the end of this exercise, you write out a formula which tells you what the value of the partition function is given the metric of the value. By partition function, we pass integral of the conformal field theory on this math, on this two-dimension. Okay? This is an extremely important, and as you can see, totally non-trivial statement. Okay, so let me try to start outlining how I want you to go about this. It's an important exercise. It's dealt with in Kolchinsky. I want you to do it yourselves, but if you can't and you have trouble, we'll discuss it with us. But let me start by outlining this. The first step in this exercise is to show T mu is equal to C by 12. So what's going on here? We've got a conformal field theory. And its stress tensor in flat space is stressless. We argued for that, we used it a lot. Now the claim is that if this conformal field theory is non-zero central charge, it would be inconsistent for the stress tensor to be zero when the theory was studied on every term. Okay? But while the stress tensor is not zero, what its value is, the trace of the stress tensor, what its value is independent of the state in the theory. Independent of the particular solution at hand, it's the same for the vacuum in any other state, and is given just by the curvature of the manifold in question. This is the claim. Do you understand what the claim is before we go on to try to explain how you can try to prove it? Okay?
Okay, this is on any manifold, which is what is the condition of manifold?
Well,
Any holes.
We're looking at, this is a local state. So as long as it's a manifold in the neighborhood of your point, you don't care anything about what's happening far away. But it's not. Okay, how are we going to prove this? How are we going to establish this? Well, you see, the first thing that we're going to do is to say, well, this is a statement about a conformal field theory in flats, on an arbitrary curve manifold. But we're familiar with how conformal field theory works in flat space. So can we convert this statement into a statement about the behavior of CFTs in flat space? And that we can. That we can from the definition of the stress tensor. Okay? So let us remember that when you go back and trace through all the definitions, all the factors that we used, our definition of the stress tensor was as follows. It says, suppose you have some correlation function, O1 over n, blah, blah, blah. Okay? Let me be more precise. Suppose we take integral dx into power minus s and some operators, blah, blah, blah. And we take that and we vary the metric of the theory a little bit. So the change in this correlator upon a small variation of the metric is given by the following. Is given by integral dx minus 1 by 4 pi integral ds into the power minus s, the same O1 over n times square root g delta g mu nu times dn. All of this is inside the objective.
Okay.
Yeah. Okay? This was our definition of the stress tensor. We'll apply this definition of the stress tensor at the moment, but there are no values, just to the partition function itself. Okay? So, a special case of the definition of the stress tensor was delta of, let's call it z, is equal to integral dx e to the power minus s times square root g delta g mu nu d mu nu. Okay. Now, oh no, sorry, I made a mistake. We would, in order to print this, I don't want to apply this to. I'm going to apply it to the insertion of one trace of the precedence. Sorry. So delta of, let me call this expectation value d mu mu. Okay. Now the next step. Okay. Now the next step. What I'm going to do is to choose a particular form. Of this delta g. I'm going to choose delta g mu nu. Okay. So I'm going to work around flat space and choose delta g mu nu to be equal to e to the power 2w times g. Times theta. So, just do that. W is small. I'm going to change my metric to e to the power 2w times g mu nu. W will be small, so the change is 2w times theta. Okay, I plug this in here. And I find the formula, the delta of t mu mu at x is equal to, okay, so the change in t mu mu at x, when I change the metric from eta to eta plus 2 omega times, take this conformal factor scaling, is equal to, and now I work the leading order in omega. Okay, so I'll drop the square root g, this is dx e to the power minus s, times there's a factor of 2. I've dropped my 1 by 4 pi, so that becomes a minus 1 by 2 pi. Okay, times t of y, t mu nu of y, t mu nu of y, t mu nu of x, integrated omega of y integrated over y. Is this clear? Okay? Now, at the next step, what you do is take this statement here and expand that to leading order in omega. Okay? So the leading order in omega, T mu mu, which we claimed was CR by 12, that we just have to expand R to leading order in omega, and I'm going to ask you to look up the factors. I will plus or minus 2 tenths. I think plus 2 tenths squared. Okay. Okay, so if we were working just infinitesimally near flat space, okay, then the demonstration that this statement is true would be the same as the demonstration that this statement were true infinitesimally near flat space. Is the same as the demonstration that minus 1 by 2 pi T mu mu of x T mu y is equal to C by 6 L squared of delta y. This is the thing we have to do. Well, at least this statement being true requires this is true. Okay? We can also argue that when this is true, we can show that it's true. Okay? But at least this thing we want to first check. Okay, so the question we're asking, so we want to show I hope this factor of 2 and the sign is right. That depends on this thing which some number, but I think that's right. So I could look it up, but okay, that's fine. So we want to show that T mu of x, T mu of y is equal to minus C pi by 3 del squared of delta x. Okay, now how do we address such a question? Okay, how do we address such a question? Well, so far in all that we've done, we've said nothing about the trace of t. We just set that to 0. That thing was just 0. We know a lot about t, z, z, and a lot about t, z, z, z bar, z bar, but we know nothing about t, z, z bar. That's 0. Certainly the expectation value of that operator is 0, but could it be somehow that there exists such an operator? That there is forced to exist such an operator, a non-zero 2-point function, even in flat space? Well, let's see. The claim is that yes, that you see, this 2-point function is very small. It's non-zero everywhere except the contact points. Such things are very subtle. These things are associated with curing divergences or things associated with regulation of quantitative theories, and are very subtle to get right. Okay? So of course if we got some nice power off or off, that would have been a gross violation of everything that we've been talking about. It would just be inconsistent. But all we want is contact term. It's very hard to get right. So it could be that when we do things and define it correctly, there should have been this contact. Now I'm going to argue for you that we're forced to have such a contact. Okay? And the argument, okay, I'm going to outline this for you soon, and then I'm going to ask you to try to fill it up. Next time in class, maybe I'll give you another way of thinking of it as well. Yeah. Okay, we won't finish everything.